recall from calculus of single variable that if we have a function g of x, then the derivative of g at x is equal to a is given by the limit of g of x minus g of a over x minus a as x approaches the value a. How about if we have a function of two variables? We introduce now partial derivatives where we compute for the derivative with respect to one variable at a time. For the first part, let's take the derivative with respect to x. Consider any function f of x, y and any point a, b. If we want to differentiate with respect to x, then we must treat y as a constant and not a variable. Since we are given a point, then let us fix y is equal to b. So in the function f of x, y, we can replace y as the constant b, and thus we have f of x, b. But what is this now? This is just a function of one variable x. For us not to be confused, let us write this as the function g of x to remind us that the function is all in terms of x now. Then let us get the derivative of g at x is equal to a. Let us use this definition from the recall. It is the limit of g of x minus g of a all over x minus a as x approaches a. So we can just copy it. But what is g of x? From what is highlighted, it is just equal to f of x, b. And thus we write f of x, b here minus g of a. Same thing, g of a is equal to f of a, b, and then copy the rest all over x minus a. The derivative of g prime of a is what we call now the partial derivative of f with respect to x at the point a, b, and it is written as f sub x of a, b. There are several alternative notions for partial derivatives. If z is equal to f of x, y, then the partial derivative of f with respect to x are written as f sub x of x, y, or these three notations which uses the symbol partial of f with respect to x. For our first example, suppose we want to solve for f sub x of 1, 1, given f of x, y is equal to 3x squared over y plus 4x y squared. What we will do is treat y as a constant, then we differentiate. So first, we note that f of x, y can be written as 3 over y times x squared so that we can see clearly which is the constant part and which is the variable part. For the last term, we have plus 4y squared, that is our constant term, times x. Thus, if we are now going to differentiate with respect to x, for the first term, first we will just copy the constant 3 over y, then the derivative of x squared is equal to 2x. For the second term, we have a constant times x, and the derivative of that is just the constant. Hence, we just copy 4y squared. And then we simplify. That is equal to 6x over y plus 4y squared. But we are solving for f sub x of 1, 1. So now we substitute the values x is equal to 1 and y is equal to 1 to what we obtained in the previous line. And if we simplify this one, we have 6 plus 4 or simply equal to 10. For example number 2, we now solve for the partial derivative with respect to x of f if our function is equal to sine squared times 2y minus 3x. Again, what we will do is first we treat y as a constant. It is not a variable, and then we differentiate with respect to x. First thing that we will do, just so to make it easier for us to differentiate, is first write sine squared of 2y minus 3x as the square of sine 2y minus 3x so that it will be easier for us to get the derivative. The derivative of this is equal to 2 times copy the whole term inside the bracket, 2 times sine of 2y minus 3x, and then chain rule for sine 2y minus 3x. What is the derivative of sine again? It is cosine. So we now write cosine 2y minus 3x. And then use chain rule further for 2y minus 3x. The derivative of 2y, again, y is a constant. So 2y is just a constant. So its derivative is equal to 0. And the derivative of negative 3x is negative 3. And then we are left to just simplify. So we have negative 6 sine of 2y minus 3x times the cosine of 2y minus 3x. So that's it for the partial derivative with respect to x. We treat y as constant and then we differentiate. Before we proceed, please pause the video and try to answer these exercises. For the second part, we now talk about the partial derivative of f with respect to y. So let us compare the partial derivative with respect to y from that of x. From part 1, we learned that to solve the partial derivative with respect to x, we need to treat y as a constant and then we differentiate with respect to x. On the other hand, for the partial derivative with respect to y, we now treat x as a constant, not a variable, and then differentiate with respect to y. If we are now going to compare their limit definitions, the limit definition of f sub y includes a function in terms of y. Therefore, the numerator is, instead of x comma b, it will be f of a comma y. All over, instead of x minus a, we have y minus b. In addition to that, the limit now goes from y as it approaches b. And of course, the notation from f sub x, or this partial of f over partial of x, will now become f sub y, or partial of f over partial of y. For our example, let us solve for the partial derivative of f with respect to y at the point 1, 1, given that our function is equal to 3x over y plus 4x y squared. Since we are going to solve for the derivative with respect to y, we treat x as a constant. So let us write the function f first, such that the constant can be clearly seen from the variable. Here, let us write 3x times 1 over y plus 4x times y squared. So that if we're going to get the derivative with respect to y, first copy the constant 3x and then let us get the derivative of 1 over y. What is the derivative of 1 over y? It is equal to negative 1 over y squared. If that is not clear to you, you can see 1 over y as y raised to negative 1 and then get the derivative from there. Let's proceed to the next term, plus 4x. 4x is just a constant, so copy, and then get the derivative of y squared. The derivative of that is just 2y. Then simplify. We have negative 3x over y squared plus 8xy. But we are solving for the derivative at the point 1, 1. So input now the values x is equal to 1 and y is equal to 1. Simplify, we have negative 3 plus 8, or simply 5. Before we proceed to the next part, pause the video and try to solve these exercises. We can also solve for the partial derivatives of functions of several variables. Suppose we have the function e raised to xy times ln z. To solve for fx, we treat y and z as constants. So let us just write the function f such that we can clearly see which are the constants. Constants here are y, ln z, and of course e. Then, we differentiate with respect to x. Recall that the derivative of e raised to x is itself. Therefore, we just copy e raised to xy. Then let us use chain rule on xy. The derivative of xy with respect to x is equal to y. Then ln z is just a constant, so just copy ln z. And let us just write it this way, y times e raised to xy times ln z. To solve for fy, we treat x and z as constants. Similarly, to solve for the derivative with respect to z, we treat x and y as constants. I leave it to you as an exercise to verify that f sub y is equal to xe raised to xy ln z and f sub z is equal to e raised to xy all over z. Now for the last part, we have higher order partial derivatives. Let z be equal to f of x comma y. Observe that the partial derivatives of f with respect to x and y are also functions of x and y. So we can also consider their partial derivatives. For example, suppose we have this f sub x, or the partial of z with respect to x. Then we still want to get its derivative with respect to x. We write this as partial square z over partial of x squared, or also written as f sub x. Same goes if we want to get the partial derivative with respect to y of fy. It is written as partial square z over partial y squared, or as f sub y. How about if we want to get the partial derivative of f sub y with respect to x? It can be written as partial square over partial x, partial y. But be very careful. If we want to write it as f sub the variables, this is written as f sub yx. And if we want to get the partial derivative of fx with respect to y, then it is written as partial square over partial y partial x, or also written as f sub x comma y. These derivatives are called the second order partial derivatives of f. In writing the mixed second partial derivatives, especially f sub yx and f sub xy, take care about the nuances in the notation in terms of the order that we write the variables. Analogous definitions can be made for functions of 3 or more variables and for third or higher order partial derivatives. Let's proceed to the example. Suppose you want to solve for the partial square of z over partial y partial x if z is equal to x cubed plus x squared y cubed minus 2y squared. This notation means we get the derivative first with respect to x, then after that, we get the derivative with respect to y. So let us get first the derivative with respect to x. If we want to get the derivative with respect to x, we treat y as a constant. So let's take that in mind. Y is just a constant. The derivative of x cubed is 3x squared. The derivative of x squared is 2x times y cubed. Y cubed is just a constant, so we are just going to copy it times y cubed. Again, y is a constant, so 2y squared is just a constant. And the derivative of that is 0. Now that we have the partial with respect to x, let us now get its derivative with respect to y. So this time around, we now treat x as the constant. And now the variable is y. So 3x squared, which is just a constant, has a derivative 0, plus 2xy cubed, again x is a constant, so just copy 2x and then get the derivative of y cubed, that is times 3y squared. We can disregard the 0 on the last term and then simplify. We have 6xy squared. For our last example, let us find f sub yxz if our function is given by x ln 3y minus z plus 2x times the square root of x plus z. So this time around, our function is of 3 variables. The first thing that we will solve is f sub y. Let us treat x and z as constants. So x is just a constant, so in the first term, we can just copy first x times the derivative of ln 3y minus z. The derivative of ln is 1 over the term inside ln. So we write 1 over 3y minus z. And then before we proceed to the second term, let us finish this first using chain rule. Chain rule on 3y minus z. Again, y is the variable, so the derivative of 3y is 3. But the derivative of z, which is just a constant, is 0. So we have 3 minus 0. The second term is 2x square root of x plus z. Since x and z are constants, then this whole term is just a constant. Therefore, its derivative is just 0. Let us just write this as 3 over 3y minus z times x. So that when we proceed to f sub yx, here, if we differentiate with respect to x, that means y and z are just constants. So 3 over 3y minus z is just a constant. So we have here constant times x. And the derivative of that is just a constant, 3 over 3y minus z. Let us write this as 3 times 3y minus z raised to negative 1. So that in our last step, when we differentiate with respect to z, we can easily see that the derivative of the last expression is equal to negative 3 times 3y minus z raised to negative 2. Then finish it using chain rule. Note that we are differentiating with respect to z. So y is just a constant, therefore the derivative of 3y is 0, and the derivative of negative z is negative 1. Then simplify, we have 3 all over the square of 3y minus z. For our last set of exercises for this video, pause the video and try to solve the following higher order partial derivatives.